start recording. All right. Welcome everyone at the Multi-Network Community Sync. It's May 24th. Agenda today, we are continuing discussion about DRA, and if time allows, we can continue talking about the CAP. If there's any other agenda item, please add yourself just probably before the CAP discussion, because this one usually takes most of the rest of the meetings. And I think, Patrick, you're first. You kick it off. Do you need to present?
I have slides, so if you can
okay,
enable
perfect.
screen sharing for me, I can show those.
Spotlight make. I will make you just co-host Spotlight. Yeah, I will make you co-host. Yeah, you should be able to.
Okay. So just let me know. I think it's still rendering for me. There's the first slide. So yeah, this is a presentation of the general concepts and features of dynamic resource allocation with some twist of some additional thoughts at the end, where we can spend as much time as we have on discussing how it relates to multi-network. So my name is Patrick Ohly. I work for Intel on upstream Kubernetes. I'm currently mostly focusing on dynamic resource allocation, besides some other maintainer activities that I'm also responsible for in Kubernetes. Well, let's get started. I assume all of you know most of this here, but this is usually where I start explaining what the current resource model in Kubernetes is, because it defines exactly the things that we are trying to improve upon in dynamic resource allocation. So first of all, resources are local to a node, advertised by kubelet. It's a simple model of things that are countable and linear. So kubelet and scheduler can make assumptions about how it can split up some resource, and resources are specified in the pod spec as something that belongs to containers. That already, for you, it probably becomes a problem when you're talking about network resources, a network card, because that is something that is shared between containers. Resource types, CPU and RAM are the obvious ones. CPU, they also are considered native resources. The extended resources, that's where we have some extension mechanisms in Kubernetes. Those are identified and advertised, or discovered by device plugins, advertised by kubelet. But they are still fitting into that model of a single counter, some number of things, basically, on a node. Already mentioned that the scheduler makes assumptions about these resources during pod scheduling, and it can do that because it also doesn't need to consult with anyone else. There is a scheduler extender concept, but it's fairly limited. It's ultimately still the scheduler that decides a pod fits onto a node, then it subtracts all resources used by that scheduled pod from the available resources on node, and then it knows how much is left and it can continue scheduling the next pod. So this is whoops, now I'm skipping some slides that I wanted to show, probably because they are hidden. Let me see whether I can go back to my editing page. Sometimes that does it for me. I wanted to show this slide here. Unhide slide. Well, I don't know why it does that to me. It happens all the time when I'm editing something. Let's see whether it's work better now. So DRA is an attempt to overcome these limitations that I just mentioned. It's a rethinking of what a more flexible resource API could look like. And the use cases that we have in mind are for things, for example, that aren't local to a node. Something that is connected to a node on demand through the IP network, like an IP camera, or through some special hardware, like a net internet interconnect, like a CXL might be examples. These are things that can't be managed by a single kubelet. So we need some different way of tracking how much of those are available in a cluster. Then we have more complex hardware nowadays. GPU accelerators are the main example that we currently have, and is also the one example or one actual implementations that we currently have for Intel and NVIDIA GPUs. Those GPUs are more complex. A single slice of a CPU has multiple aspects to it, like how much compute RAM, how much RAM it has, how many compute units, and then there are different types of GPUs with different features. And those aren't even integers. It's a feature flag basically that says, this GPU can do this or that. And these are things that must be considered in combination to select a suitable GPU for a pod. And then another use case is specifying somewhere in the Kubernetes API additional parameters that are required to pre-configure that hardware. The FPGA example is listed here. We typically need to, of a programming as FPGA is typically a privileged operation, something that we don't want to allow individual programs to do themselves, because that would imply that we need to give them full access to the hardware. Instead, the driver needs to set up the FPGA first, load the program, then hand over a device, identify the device node to the program with less privileges, and then the application can just use the pre-programmed FPGA. But that means we have to have some way of specifying, say, a URL where to load the program from. That needs to fit into the API because the user needs to supply that. Finally, the sharing of resources needs to be a lot more flexible. We might have the multiple different containers in the same pod that all need the same GPU instance. That's one example. Or if it's an expensive or something that's expensive to set up, like an FPGA, we might even want to share that same pre-programmed FPGA between different pods, either concurrently or one after the other, depending on what's more suitable for the workload. And all of that needs a different API to define those relationships between containers and the resources that they're using. Another term, another technology that you'll see mentioned is the container device interface specification. That's a lower level thing. It's almost like an implementation detail in DRA. It's a JSON spec supported by container runtimes that enables someone to inject additional resources, volume amounts, device nodes, environment variables into a container using a JSON description of what is supposed to be added. And that makes it possible for a driver to basically explain to the runtime what it needs to do without having to modify each individual runtime to support a new hardware category or device. This all is a Kubernetes enhancement proposal. The cap number is at the bottom of the slide. Because we are touching core Kubernetes, so it had to be a cap. The way how it works is fairly similar to volumes. We took a lot of lessons learned because I've also been working in SIG storage before, modeling our APIs and object types after the persistent volume claim and the volume class that exists in SIG storage. The resource class. If you have questions, feel free to interrupt, or I can keep going. We can come back to the slides. So anyway, the resource class is the privileged object created by an admin when deploying support for certain hardware together with a resource driver. And the resource class has parameters that are known to be privileged. So these are things that normal users shouldn't be allowed to set. Something that gets chosen by the admin, and it also ties a certain resource category with a specific implementation through the driver name. This is like a CSI driver in a way, a container storage interface driver. Then the resource claim, that's the separate object created by the user together with his application. And the resource claim is where the user can specify parameters, basically his requirements for the resource. And that's a difference compared to how it's done in SIG storage. We are also using the resource claim status to store information about the actual allocated resource. That simplifies a lot of things. A lot of problems in SIG storage nowadays are around synchronizing the persistent volume object and the persistent volume claim object. And there are still cases where you can have leaked volumes when something gets deleted at the wrong time. And it's a fairly complicated dance with lots of finalizers to prevent things from happening that just are difficult to track because it's two different objects. There was a cap in Kubernetes a while back that said that status is also okay to be used for information that can't be restored from some other state. That's why we can do this. It wasn't possible before because status was supposed to be something that is ephemeral and can be restored, but not anymore. We can do that. And finally, the pod that has some additional fields that references a resource claim, and I'll give you an example on the next slide. So another key concept is that these parameters, although resource class and resource claim, these are core objects, or rather they are built-in types in Kubernetes. They are not in the core V1 API, but rather in a experimental V1 Alpha 2 API that we defined, the resource.kas.io API group. But this is built in. What isn't built in is how to represent parameters. Those are not embedded inside those objects, but rather in separate objects, typically defined by a vendor CRD. So you get full validation of the parameters at the time of creating them, which is nice for users because if they make a mistake, they will get very early feedback from the Kubernetes cluster that something is wrong. Another concept is the communication between scheduler and resource driver. I'm trying to avoid situation or trying to keep the deployment simple. So all I'm requiring is that a resource driver can connect to the API server, and all communication goes through the API server in a shared pod scheduling context object. That also has the advantage that multiple different drivers can collaborate on the same object and work together to pick a node. The actual protocol is a bit more involved. It may involve some back and forth between scheduler and driver, but so far it's working fine. And I've already mentioned the allocation state that is in the claim status. So here's an example. There are multiple different objects involved. That's the downside of the flexibility that we had to have, but we were basically asked during the API review of the initial implementation to really just limit our modifications to the core API to very few fields. So that's what we have added. The containers have under resources a new claims array that's ultimately just a list of names. And the name here is internal to the pod chosen by the user. The resource type or resource name refers to some other new array, the pod level resource claims. And that is where we define where the resource comes from. Directly referring, as in this example, to some existing resource claim is one option. The other option is to have reference a template, a resource claim template, and then there is some additional tooling in Kubernetes to create an actual resource claim from the template for each individual pod. That's what you would typically use if each pod needs its own resource. The example here could have multiple pods, multiple different pods, all sharing the same resource claim instance. So the external claim name, that is the name in the same namespace for security reasons of a resource claim. The resource claim then references the resource class. It doesn't really do much here. And that's where we have the test driver. That is something that we have in tree to test out the array. So this example is also not that realistic in the sense that we are using a config map of predefined type to store parameters. And the resource claim, that's the last connection here that I just highlighted, is from the resource claim to the config map in this case. But that typically, that instead of config map, it would be a CRD, something that defines exactly what the parameters are. And then the API will be a lot nicer. It will not be just a string to string map as in a config map, but it could be arbitrarily complex. You could do hashes, lists, could do validation through the normal mechanisms for a CRD. And my last slide is trying to show how that could look like for multi-network. But I suggest that we first go through the rest of the DRA part, if that's okay. But is there a question here? Per, I see that you unmuted. So if you have a question, just shoot. Nope. Okay. Yeah, this is an overview of the components and the types that we have had to add in Kubernetes. So what the KEP is about is the left-hand side, the core Kubernetes changes. Obviously, we need to add new types to the API server. Resource claim is shown here as the core object that everyone interacts with. The resource claim controller inside the controller manager, that is what handles the resource claim templates. But pretty much everyone else then just deals with resource claim. It's a unified approach to generating resources for a pod. Instead of having two different code paths, basically everyone just waits for the resource claim to show up and then works with that. And the resource claim controller is the one that is the only component that actually deals with a template object. The scheduler has a new plugin built in that knows about resource claims. It, in the filtering stage, looks at resource claims and whether they are allocated. It collects potential nodes by working with the other plugins. And then in the scheduler reserve phase, the resource plugin is called again. If a resource claim hasn't been allocated yet, we can't proceed in the reserve phase, but we can do what's called delayed allocation. At that point, the scheduler knows roughly where the pod could run. It knows about the available CPU and RAM. It knows about other volumes, for example. And then the resource plugin, if that is insufficient information available, can say, okay, let's create that resource claim for that node. That's where the pod scheduling context object comes in. It's not shown here, but that's what the resource plugin creates and what the vendors then react upon. They see that a pod scheduling context object exists with, say, a selected node, and then they try to trigger the allocation. There's also a mode with immediate allocation where the resource drivers don't wait for a pod to show up, but that is probably less useful, and we expect that most resource claims will use the delayed allocation and wait for the scheduler to make some preliminary decisions about the node. One key goal that we have for scheduling is that we never schedule a pod onto a node unless all resources are really available. For CPU and RAM, that's something that the scheduler can guarantee. For resource claims, we achieve that because we expect the resource driver to do some real allocation, set aside the necessary resources for that resource claim and therefore for the pod before the pod gets scheduled. And the scheduler is waiting for that. It's waiting for that status change when resource claim that says, this is allocated, you're ready, now you can schedule. And then the node local operations, those are supposed to be so easy that it's unlikely that they ever fail. So the kubelet part, that becomes relevant as soon as scheduling is done and the pod has a node name set. Kubelet knows about the resource driver kubelet plugin. It's a normal registration mechanism, but with a different API. There are two API called two gRPC calls, preparing resource and unpreparing it. And that happens when some container starts to run on the node that uses the resource claim. That's where the resource driver might set up some device nodes, prepare a CDI file, and what it reports back to kubelet is the so-called container device interface ID, a simple string that kubelet just passes through to the container runtime. And container runtimes know what to do with those IDs. They basically read the JSON file, apply the necessary changes to the container, and then the application can run.
Can I have a question to the previous one?
Yeah, sure.
The API server, this is the scheduler side. Is there any, at any point, does the scheduler calls to the resource driver?
Only indirectly. So I probably should have a slide with a pod scheduling context object, because that's where the communication between scheduler and resource driver happens. So the scheduler, before it selects a node, it knows that there are resource claims that haven't been allocated. It knows that those resource claims are waiting for a pod. And what the resource plugin then does, it creates a pod scheduling context object. Initially, that just has a list of potential nodes as identified by the first attempt to schedule a pod. And that ignores where resources are available, because that wasn't known at the time yet. The resource driver then sees that the scheduler is trying to schedule a pod. It sees what pod nodes might be useful for, or might fit for pod. It can reply with a separate list saying, okay, I checked your nodes, but these are unsuitable because I don't have resources. And that it reports back in the same pod scheduling context object. So ultimately, that pod scheduling context object will have information from all resource drivers that are involved with that particular pod. It might be more than one. The pod might have two resource claims that need to be allocated for it from different vendors. But yeah, that uses the same pod scheduling context object. And then the scheduler watches for changes of that object, triggers another scheduling attempt for the pod. And now it has more information. It sees that, okay, these two drivers that I'm waiting for, they both agree that this node here is suitable. Let's try to allocate for it. And that's where they set the scheduler plugin again sets the updates for pod scheduling context object and updates it with the selected node name set. That again means scheduling needs to be aborted at that time. It's an iterative process. So it's slower than normal pod scheduling, but that's a price that has to be paid for the flexibility that comes with parameters that are entirely under the control of a vendor.
So, and that's the last thing that you said. That's why I'm asking. It does rely on the external controller here, right? Is that true?
Yes.
Let's assume. What I'm getting at is, let's assume we have all the resources for a pod, right? So there is no contentions, no nothing, no race. And I'm just scheduling a pod. Now there will be an additional gRPC call and the processing, and you said it's indirect, but it's still in the scheduling process. That will be made to an external controller, which has to return and process and provide me information. So basically and what I'm getting at is the moment from kubectl apply to the moment where pod is ready.
Yeah, that is so certainly going to be, that is slower. That's certainly going to be slower. Yes. There is additional latency here.
And it will be dependent on some external controller in this case.
Yes.
Is that true?
Yes, okay. That's true. But that's the key problem that we are having here. We can't assume that the scheduler knows what the resource claim parameters
that's
mean.
given.
There's no way how we can build that into the scheduler. People have tried to come up with some taxonomy of fairly flexible generic resource parameters. But the problem is there are always some limitations that you can't model, or you forgot to model, and then you need to update that model permanently to adapt to new hardware. We're not even trying that. people.
No. That's the whole
Yeah.
I think of your DRA. That's
Yeah.
the whole selling point, that you can.
It's the entire
flexible.
parameter handling is on the resource driver side.
Yeah.
So
Okay.
let's talk about that perhaps for a second. So it does need two parts now. The device plugin mechanism only had one. It only had a local kubelet part. Here we have a controller part, the part that interacts with the scheduler, and we have a local part on each node. And those also need to communicate between themselves somehow. We have an example driver that is again using a CRD where it's publishing node state in a CRD for its own internal consumption. So that's not, it can get documented, so users can query the state of that hardware, but it's outside of DRA. It's entirely defined by the vendor. Okay. Yeah, short history. This has been a discussion for a while. It started actually with CDI, an effort between NVIDIA and Intel, starting at the lower level parts, just talking with runtime developers, what that JSON spec should look like. Some container runtimes adopted it and implemented it. And then middle of 2021, we started talking about how to do the Kubernetes part, leading up to a first KEP draft that got accepted into Kubernetes 1.25. And we got to the point where it was declared implementable with some caveats, some opens. But and there also was a prototype that I had been implementing along with a KEP, but the KEP got merged fairly late, and it had some changes that just made it impossible to actually get code into 1.25. Instead, I proposed something fairly early for 1.26, but because it was such a big change, we had problems getting reviewer intention. It got merged eventually. It certainly wasn't easy, but it got merged as alpha in 1.26. And it has been in alpha since then, because we are now exploring use cases, addressing review comment that came out of those review periods from 1.26. We're still working on those, and we have various opens for beta defined in the KEP that we still need to work on. The other thing that happened, I'm mentioning Intel here because I'm Intel, but NVIDIA also had a public alpha quality driver for their hardware that is based on DRA. So depending on your hardware, you can use either the one or the other. In 1.27 Kubernetes, we did improvements, cleanups, benchmarks were added. The example driver that I mentioned, I have a link at the next slide somewhere, that got published for KubeCon this year. And there was a presentation at KubeCon Europe where Kevin Clues from NVIDIA and Alexei Formey talked about that example driver and how to implement a DRA driver. So that's what happened this year. And now big open, well, some opens, schedule enhancements are necessary. I mentioned that multiple pod scheduling attempts are needed for a single pod. The way how the scheduler currently handles that is that it inevitably puts the pod into backoff queue. There is a 5-second delay. That's completely unnecessary, but that's how it happened. Currently is being dealt with. And I have PRs pending that eliminate that backoff period, because it's normal for such a pod to need multiple attempts. It's not an error condition that someone means that the scheduler needs to slow down for this particular pod. And these enhancements are pending. There is also some other proposal along the same line. And one of those will probably be merged into 1.28. Then beta criteria also include defining how the cluster autoscaler could work with a workload that involves dynamic resource allocation. The traditional model is cluster autoscaler uses the same plugins as kubescheduler. It therefore knows which pods fit onto nodes. And that's no longer true for dynamic resources. So we are thinking about some kind of plugin mechanism for the autoscaler. It can't be exactly the same because that would be communicating through the API server, and that clearly would be disruptive for the rest of the cluster. So that's where we may end up with direct gRPC calls or Wasm plugin or native plugins that need to be compiled in. It's a bit open at this time. But I had discussion at KubeCon Europe with the cluster autoscaler maintainer, or one of them, about this topic, and we'll pick that up. And then eventually, if we solve all of these technical questions, and one of those I think we also is something that we want to address, is about CNI and how this could be used for networking. Eventually, we'll hope to get GA perhaps in 24. So that would be, yeah, Kubernetes 131. It's certainly a long road, but that's inevitable because it needs time to get feedback, incorporate feedback, make changes. That's just the way it is. So I'm not going to do a demo today. I think our time is better spent on discussions than just me walking through some shell commands. If you are interested in a demo, I encourage you to go to this repo here, Kubernetes 6/DRA example driver. That has full instructions for bringing up a kind cluster, so no real hardware needed. And the example driver simulates a GPU driver, so it's more realistic than what we have in tree. And then you can see how this all works in a multi-node cluster, just on your normal development machine, assuming that you have Docker on it and running Linux or Mac OS. On the right-hand side, you can see where you can find us if you have other questions. So there is the main channel that we're using on Slack is the SIG Node channel, because SIG Node is the sponsoring SIG for this work. We have regular meetings if you want to be involved in those. We have one on Monday where we talk technical questions around DA with our counterparts in NVIDIA. There's also the CNCF Container Orchestrated Devices working group where CDI gets discussed. And here's a list of names, just for your information if you need to ask specific questions or want to associate some names with this project. Here's all the people that have been working on this, both from Intel and NVIDIA. And I think, well, if you have questions around DRA, we can discuss that now, or we can move on to my rough ideas how that could work with multi-network.
Oh, if you have something more than yes, please, let's move on to
yes,
that.
I do. So you might remember this slide here, how it looks like for DRA at the moment. For multi-network, it wouldn't be that different. One difference is that these resources probably, and I'm speculating here, are not associated with individual containers because the network is something that gets set up for the pod. So we need some kind of concept for pod level resources, something that only shows up once here and doesn't need to be referenced in the containers. That would be the first change that we somehow need to achieve. But it's doable. We had some ideas whether it could be some result in the status that tells Kubelet that this is a pod level resource and then triggers some slightly different behavior. Or it could be in the template, in the resource claims, a new field that says, yeah, this is a pod level resource. Both options probably would work. Then I want to call out that now I'm actually using a CRD for the parameters. So multinet KAS.io in a very first V1 Alpha 1, that would be something that your working group could own and control and define with a spec that has parameters that are required to be supported by different hardware vendors. I think that mirrors what you are trying to do with in-tree API, something that all drivers somehow need to support. But it could be a CRD, so you wouldn't have to do that in tree. You would have more flexibility with this approach by being out of tree, at least in the experimental phase. If you feel that at some point these parameters need to be in tree, nothing is going to stop you from writing a cap, creating or asking the API reviewers to approve a new API group and make that an in-tree type. The advantage of that is that it actually would be rolled out using the normal Kubernetes deployment mechanisms. It's currently still fairly problematic to have core API is defined by CRDs because the upgrade path is unclear, deployment installation is unclear of those CRDs. It's an unsolved problem that also SIG Storage has, because the snapshot API that they defined, that's a CRD. And even after several years, they still don't know exactly how to convince everyone who installs a Kubernetes cluster to keep that CRD updated. The other difference, of the other part that I want to call out, is that this is basically, could be a common API supported by different and implemented by different hardware vendors, and the resource class mechanism could be used to select the actual implementation for that abstract API. And you could define that there must be in each cluster a resource class. I think I forgot. Well, the name could be standardized too, and then the contract between the hardware vendor and the user would be that a resource class with multinet.ksio as name must support these parameters. It must do something useful and must do something specific that is defined by your standard or by the working group. So that's all fairly genuine. It's not requiring many changes in DRA. Where it gets a bit more interesting is handling in kubelet. What do we actually do at the kubelet level with such a resource? So one idea, and it's not specified anywhere. This usage field is new. It's really just an idea, a proposal that I haven't even formulated somewhere. I did create a pull request with some experimental changes at the bottom of a slide. Is something that I started discussing with folks, and it has in a one comment, it has this usage field. But I'm not sure what the right approach is. And I also must admit that I don't know that much about CRI and CNI and where the information needs to flow. Others know that better. So we could have, what right now kubelet does this node prepare call when it sees a container that references the resource claim in the pod. For pod level resources, we could change that so that if there is any such resource claim even if it's not referenced individually by containers, then it could do the preparation and it could handle other additional data, something that the plugin wants to pass into CNI somehow. All of that could go into the resource handle, or it could be part of the gRPC interface. All of these are up for debate. The big gap that I see is the question of how you could then deal with this and how you could build additional APIs or additional behavior in core Kubernetes around this. And I don't have a proposal for that, to be honest. So we could standardize on certain fields in the resource claim status. So for example, this data field here that I'm showing the right-hand side in the resource handle. So that's part of the API. And it would be possible to have some specification that says this data field in a network resource, in an allocated network resource, must be in a certain format. And that could be something that could be read and interpreted by other components. But I'm really thinking aloud here. I don't know whether that is suitable. But yeah, that's
on that yeah. part. We would really need something like pod status with IPs, right? Pod IPs. There is something we need that kind of level of integration for that, because and this is another I gonna start poking holes. Sorry, Patrick.
sure.
How it's a quite good idea where you had this network CRD. I agree, that's nice, because then it's flexible. We are not in core and our development is unstifled. But how do I deal with services? What do I reference? They will not allow me in service to reference an ACRD. So that's my first problem. And I don't think we want to put resource claims into services now. Now, what I do with network policies, the same story. I need to have, and then those are just the two first. Now I have ingress, gateway API. I have at least those two things that are top of my head that I need to not only pod, because pod is just the first element that we are currently tackling, because that's the core kind of. But if you look at our list of requirements, that's just the first phase, right?
Yeah.
And then we need to integrate with the rest of core Kubernetes. Yes, resource claims is nice ways of implementing the thing. And I assume that you were saying about the usage, the CNI, that could be an optional thing, where not maybe fully optional, because in our current approach, it's flexible in terms of how far I want to reuse CNI and how far I want to push into the CRI, and it has to be aware of multi-networking versus I'm doing it through some controller. It's CNI is just a stub as it is today, and then the rest is done by some daemon that's on the top, right?
So yeah, I think you're right, but the starting point could be this special resource handle field, and then when you would need to work with kubelet and get kubelet to populate some additional fields in the pod status, all of that could be triggered by a resource handle or allocation that has this special field.
But
and
that
then
doesn't really
that's not
fit
yeah.
into DRA itself. That's
No,
let's ask it from
it's
other side, right?
no, it's
It
not.
doesn't
It's
fit
not
at all
DRA
into DRA.
anymore. This would
So
be it would be a separate cap that basically says, okay, I'm using DRA as a starting point, and once I hit kubelet, then this is what we do on top of it. And that would be additional interaction between kubelet and some other daemon. It could be another gRPC interface that needs to be invoked by kubelet, where you pass information back and forth. And you could define those pod status fields that you mentioned. And I think that extends then what starts with DRA, but it certainly goes at some point into a territory where you have to define your own cap and define those fields, and then define the rest of what you need for your use cases.
The one thing
I like,
yeah, go ahead.
the thing I like about this that feels really good is, I think when we are thinking that a pod is going to be attached to some networks, there's some stuff in there that is just generic. It's just going to be in a network, and the network will just return an IP address, and it's not, the implementation just deals with everything. We are going to have needs where we have to pass more complicated configuration through. And this is an existing mechanism we've got where we could do that. So you don't just say, I've got this network, and the network field is going to give you whatever you need in order to do services. But in addition, here is some random bit of plumbing information that network needs. And the fact that DRA already exists and that we can just piggyback on it sounds perfect. And I mean, I haven't dug into lots of the details here, and I may be missing some of the points, so I need to go and drill a bit deeper, but it does feel right to me as an approach. It feels like it's got some real promise. So I'd like to understand it a bit better and think some more about it.
I want to point out one thing that I missed earlier that I hadn't really thought about, but you were concerned about scheduling performance. If all that you need is a mechanism to pass additional parameters, and you don't really need to influence the scheduling, then we could also extend the resource class and have a field there that says this particular resource class doesn't need real allocation. We could just handle the allocation in the scheduler and basically say, okay, well, we automatically allocate because we know that this is going to work. We don't need to piggyback through the resource driver controller unless you want to. That should speed up the scheduling quite a bit. And if depending on how your implementation works, that may be a valuable optimization. Anyway, I'm rambling. There are some aspects that need to be considered, like what happens, for example, if the parameter object gets deleted, because it is separate. That is something that the user could do while the resource claim is allocated. So we do have a concept of copying relevant values out of the parameter object into the allocation status, so that if later on the user deletes the parameter object, the resource claim is still usable. But anyway, I think there are things that we can change because DRA, as I said, it's alpha. We can still make those changes if we discuss them with you guys now fairly easily. We can still also change them later on, but then it becomes harder. Anyway, Martin,
So
you had a question. Yeah.
to the parameters kind of idea and subject, and what Pete, what you were saying, keep in mind, I would imagine the network here is the network that we talk in our CAP today, right? So the parameters will be referencing that this network object that we are seeing here. You said it's network parameters, but I need something that I can reference by the other object, as I mentioned, because the core issue isn't going away still. How I'm dealing with services, because that's the core thing here. We need to make this integrate with Kubernetes. So what I reference in services, and let's say I can reference the CRD because my CAP is going to introduce that CRD of a network, which then your resource class or something can reference a network. That's fine. So basically, now I would end up with pods referencing and using the resource claim path, and then all the other objects will just directly reference the network itself because they don't care about claims, right? They just need to point to which network they apply to. So network would be the object that we are keep discussing today, and then that one will reference the parameters itself. So Pete, that doesn't change, and it's still you have another object that you have to reference for network because you have to have some common element that you can reference across other objects. I think we keep forgetting about that one, which is the core piece of this whole. We already have a multi-networking referencing capability through Multus, and it already does that, and it already works, and we have that in production, trained across the board, and it works. And if we just settled on that, this is just a replacement for Multus, and instead of using annotation, do this. But that's not the point of the whole effort. Effort is to integrate fully with core Kubernetes. So have it across the board with all the other objects. So let's make sure that we keep that in mind. Having just a reference through a pod is not, it's just a 10% of the whole thing.
But basically in DRA, you can reference any kind of object, right? So it's the community decision will be if this, you know, L object
Any
will be in the
object,
core.
what do you mean?
You just reference something, right? In the, Petro, correct me if I'm wrong, but you just, when you create the resource claim, right? And you reference a parameter, is just any kind of object that Kubernetes is aware of it. So
no, that's fine, but that's other way around.
But if we assume that
then
the network
service on something,
you're going to have a similar problem. Right? You're still going to have the pod. And now you have the pod, adding in more. I mean,
what's the problem? I have the pod reference to the network, so I can get the network information, right?
Right.
You wanted to be in the pod. That's the. I'm trying to understand.
So now keep in mind, for example, I'm trying to maybe I am a bit, and I apologize, imposing the kind of way we are thinking about services. But what we are thinking about services is to have an ability. So service, if you think about service, Kubernetes, and I'm saying Kubernetes service here. So cluster IP, all those, right? Those. You cannot have a service across multiple interfaces. That's impossible, right? You cannot have the same IP across multiple interfaces, which belongs to different networks. That's something that you naturally can do. So a service has to be bound to a specific network and be advertised through load balancers on a specific network. So that's why I am kind of imposing that a service cannot be applicable only to a pod. It has to be applicable additionally to a specific network or interface of that pod. Unless you think that's what I'm saying.
This is represented with the endpoint slices, right?
No,
how the service.
So that's just implementation under the hood. First, let's conceptually what a service, what does it apply to?
Well, a service applies to pods in reality, right?
Thank you.
That's true today. That's true.
So, but I mean, so in reality, I agree with you. Sort of that you probably want to be able to make sure that you can access a service over a specific set of networks, but from the highest level of abstraction, I guess either can be argued.
So this is I see what you're saying. But then is it feasible? That's maybe let's boil it down to like from the
Yes.
networking point of view. Is it feasible? Like services has single VIP. Should I be able to access that single VIP through multiple on different networks? And let's even
Yes.
assume different types of networks here. We have coming from L2 to L3 network types, right? Because we want to support all of them.
So I mean, yeah, so VIP is a virtual address, right? In reality, probably can. I could probably build it. The question is more, should you?
Exactly. So this is where, and this is just one concept here. The other thing will be network policies, which probably you have even more kind of ideas here. And this is where conceptually network policies, putting aside the implementation, I know how you integrate multiple CNIs. Let's put that aside. Let's assume we can synchronize everything. But that's from the conceptual high level from network policies themselves. Today, I would agree. This is something that is more flexible here because this is just blocking things, right? So I should be able to, if I don't specify any network, I apply to a pod. And then every interface should be, let's say, block this specific networks on it, right? But then I maybe want to, as an ability, I want to network policy on this, not just on that network. I don't care what happens on the other ones. Those are internal and those should be just unblocked. But for this one specific interface, it goes into the internet or something. And for that one, I want to apply my network policy. I should be able to select with network policy a specific interface. And it should be optional on this case, but I should be able to do that. And now even for that aspect and the services, I don't want to go into, and I apologize, I don't want to go into like specific implementations of those, but conceptually, if you think about it, then I would have to be able to reference a specific interface in addition to the pod, right? Because today you can only select a pod through labels, right? And coming with multi-networking, and it was sufficient when you have only one interface in the pod, and that was perfectly fine, it worked. But if you're going with multiple networks into the pod, and now you're fully aware of them through Kubernetes core APIs, I should be able to now additionally, any of the concepts that relate to any networking stuff, I should be able to individually select one of those. And that boils down to now then, how do I do that? I cannot do it through resource claims because now I am going to put the resource claims everywhere in all those. That's kind of doesn't fit, or does it like translate, right? That at least in my opinion. So that's why this effort of this group is to introduce something core. And I saw some of the minutes from last week where Prashant was saying that we want to make this network a core API so that it can be referenced in everywhere else, not only the pod. And I do see the value of the resource claims for the concepts of like network can have QoS where it can set the shared bandwidth, for example. And I love that idea. And I would want to have that, right? Where I can, okay, I have a network and per node, I can divide the bandwidth across the pods for it, right? Because that's something that's really important and we want to have that as well. But I don't think we can avoid the API kind of aspect of the whole thing, right? Because this is the sharing of the network and QoS for it is just an additional extension. That's how I would see it. But I wouldn't just make the whole initial concept of having the centralized reference of the network be replaced by this, by just the QoS kind of advantage of this whole thing. Pete, I'm not sure yeah, I would like you to read more on this, and I'm not sure whether because you see this one as a good approach for the whole networking, but I don't think we probably can in the underlying kind of implementation do something about this, but in terms of references in the APIs, I would still want to stack with my network and sorry, the pod network that we have. And the
I
reason is
don't
for
think
that.
I don't think there's a talk of replacing the pod network so much as supplementing it, right?
I can't.
Yeah,
Mhm.
you
So-
need to think of DRA as a mechanism that you can use, but currently you can define your APIs in the core. This is what I'm trying.
Mm.
Like, it's not contradicting it. I think the point is to use DRA for networking, because you will end up in a situations when you want sophisticated resources for the networking,
Mm.
and then you will end up that you request it from DRA and you need to integrate it anyway to your networking API. So I think that the discussion here is, keep in mind a DRA as a mechanism for you, okay, to use it. Okay, now you can define the API. I think I also agree that the API needs to be in the core. This is my personal opinion, but I don't know what. The objects themselves, right? But it still doesn't mean when you request a network, you cannot do it with like a resource claim and say that this is the network that you want. Okay, and this is the only problem that solves you, the QoS and to request sophisticated resource like SRIOV and FPGA and other stuff, yes. So it will be bundled together and it will be very easy to the user, because even today you request a network and you need to specify that the resource is, with a sophisticated hardware.
And maybe that's the gist here, right? Like maybe we need to keep the way how we reference and it in a pod and basically treat it as a resource claim for a network, right? But then still have the pod network itself so that the API piece is satisfied as well, right?
This would be more the characteristics that you would specify, or the need. I need this resource, but I mean not the generic setup of the network abstraction, so to speak. If you need, like I said, if you need SRV or if you need a 100 gig interface, well, specify as a resource claim and let the controller handle it.
No, I would imagine this as your resource claim. So
But
probably it cannot be called resource claims, because then it would have to be still called a network.
No,
But
no,
the
but
underlying implementation would still be done through through this resource claiming. But then you point. But then, let me finish.
Sure.
But then you point to a pod network which uses and references a. Okay, I see what you're saying, because
No, it's like I assume that everything is in core, but then I have a pod that wants to have a. Oh, let's go even higher. I want a DD port. I want the 400 gig port. For this pod on this network. I need to have a 400 gig port. How do you specify this? That I see fitting in with as a resource claim, and sort of the scheduler will do the mix and matching to find you that card that can give you that, right?
But then you're saying that will be that would be a separate thing, or in addition to just saying I want to connect to this network.
And in addition, I would say, I mean,
I think it's almost like parameters for the network. Is
yeah, exactly.
Yeah. So you're saying not just I want to be on this network, but I want this particular bit of random internal to my implementation parameters. Here's where I can put them.
Yeah.
And in the current documentation, you have the provider that does that, right? From what I said.
Yeah, so someone will have to say, I provide these resources, right? I think that's
but see, this is fine. Like network is the common pieces, and then still you can reference a different object, which is like a specific thing that how you want to claim, like how you want, a very, vendor control. Because in most cases, when people do just networking, simple one, they just want an IP address and a very simple stuff. Yeah.
Could be something simple as I need to have, I want to have hardware accelerated crypto for the following types of
network. Yeah, for the following network request, which is a resource claim. Basically, you're requesting a network and.
Yeah. But it's a extra on top of a normal. If I just want to have a best effort, I don't really care connection. I don't have to file in the resource claim because anything is good enough for my pod.
Yeah.
And then it falls back on other things. So
and the nice thing here, yes, that like Patrick said, we can change the array that in the neutral case, right? When most cases, you know, just VTH pair, very just IP address. You don't need anything in scheduling. Nothing is going to change, and we can modify the array, not do any, you know, consulting with the controller and stuff like that. But once in the network, you know, I want an SRIOV now, or I want more sophisticated stuff, then, you know, you can also do the controller stuff because it's already built in the array. So it will simplify for us future problems that we're probably going to tackle. Yeah. So
Yeah. Before we drop, Patrick, can you host me? I had to reconnect. Can you tag me as a host? I want to kind of stop the recording as well. Make sure that it's there. You're muted, if anything, Patrick.
Yeah, I need to find the right setting.
It's in
Zoom
participants. Go to participants in
participants.
Zoom. In
Yeah.
Zoom participants, right click on my name and you can just make host or something like that. And then I think we're
Yeah,
gonna
I think I
call
got
it
it. Yeah.
here. Thank you, Patrick. Patrick, can you additionally, do you have link that you can share to this presentation?
I can post it somewhere if it's on SharePoint, so I could copy it to Google Docs if that helps.
Yeah, if you could make it externally available, I would
Yeah.
appreciate that, so we can everyone, and I will tag. I don't think I have your email, but in the agenda, if you could, if you can share it
I'll
externally
publish
and
it,
then
yes.
post that link in the agenda, I would appreciate that.
So
All
now
right.
also
Okay. I think let's digest what we discussed today and let's continue the discussion. Let's make a decision. Let's try to make a decision next week about how we want to do and deal with the DRA in this effort. Okay. We are past 6 past, so I'm calling it for this today. See you everyone next week.
Bye.
bye.
Can anyone hear me?
Bye.